and inference.
Thank you. Can you hear me? Yes. Yes. Okay. Let's just see that, yeah, everything is working. Okay, so I want to start by thanking Sanjib for this organizing this conference and for the invitation. It's just my second time in India and first time at the Raman Research Institute, first time in Bangalore. I'm enjoying it very much. So thank you very much, Sanjib, for this opportunity and to come and present before you. Okay, so my name is Shlomi Reuveni. I'm from the School of Chemistry at Tel Aviv University. And the title of my talk today is Universal Linear Response of First Passage Kinetics, a Framework for Prediction and Inference. What I'll basically try and do is advertise a recent discovery that we've made regarding the universal linear response of the mean first passage time to perturbations. So this talk is going to be about first passage time processes and how they respond to perturbations. And I would like to argue that in many ways, this response is completely universal. Before I start, I want to give credit to a highly talented PhD student who led this research, Tomer David Kedar. The paper is on the archive. It has recently been revised. And the details of what I'm going to discuss today are there and more, okay? Now, without further ado, let's talk about perturbed first passage time processes. What are they? So these are the heroes of my story today. Let's maybe start with first passage time processes. The classical example, you have a particle that is diffusing here in a flat energy landscape until it finds a target. So this is a first passage process. Now comes an almost trivial observation that you can make. First passage time processes rarely occur in isolation. So they are, in many cases, perturbed by all sorts of externalities that happen in the environment. So for example, here, I could decide that at some point I want to turn on a field. And then the dynamics that was before is no longer the dynamics that is after. The particle is going to continue diffusing. But now in the presence of a field, and of course this will affect the statistics of the first passage time to the target, okay? So we took a first passage time process and we applied the field, we perturbed it with the field, and we got a perturbed first passage time process. Simple as that. Another example is, you know, maybe I own an asset, maybe it's a stock, and I'm following its price in the stock market, and I've decided ahead of time that I will sell it when it reaches a certain target price. But then again, what could happen is that some externality in financial markets, they like to call it black swans, or a black swan will happen. This is a rare but cataclysmic event. Maybe a big earthquake, a war, the election of a controversial president will happen, right? And then the dynamics that was before is no longer the dynamics that is after. This black swan will rattle the markets. And of course, this will affect the statistics of the time it takes my stock to get to its designated price. So this is another example of a perturbed first passage time process. Another example that I'll give, which is very popular nowadays, comes from the training of neural networks. So maybe you're training a neural network to tell apart pictures of dogs from pictures of cats, or any other task that you train a neural network to do. And the point is that you're training epoch by epoch, and the neural network gets better at its task. But the training process is inherently stochastic. So what people are doing, they're using stochastic gradient descent. And the point is that the time it will take you to get to a target accuracy, say 80% fidelity telling apart a picture of a dog from a picture of a cat, is a random time. So you have a first passage time process. How much time it will take the network to get to its target accuracy. But where is the perturbation? The perturbation, people notice that, you know, they can perturb this training process by changing the weights that the network have learned in all sorts of different ways, and affect the time it takes the network to get to the target accuracy. Sometimes for the better, sometimes for the worse, but it's a perturbation. You have a perturbed first passage time process. I'll get back to this example later on in my talk. So I've given you 3 examples, but of course you can consider more. You can take your favorite first passage time process and your favorite perturbation, bring them together, you have a perturbed first passage time process. And the question that I want to ask is, how do first passage time processes respond to perturbations? And if there's anything in general that we can say about this question. Okay. So where's the motivation? The motivation comes from classical linear response. Okay, we want to do something similar to that and then maybe go beyond linear response, but today I'll talk about linear response. So we have classical statistical mechanics. We have an observable at equilibrium. It will attain a certain value. But now what I can do is I can poke the system. I can perturb with a small amplitude. And then the value of my observable is going to change in linear proportion to the amplitude of the perturbation. And the proportionality constant is the susceptibility. Okay? So the question is, can we do something similar for first passage time processes? Another example that we have here, kinetic processes. Can we do some response theory for kinetic processes? So I have here a protein. It folds. This is now my first passage time process. And I can think about a perturbation, one of many. You know, this is a perturbation that happens in our bodies billions of times every day. Maybe your protein gets stuck somewhere, and nature came up with these amazing machines. They're called chaperones. They will take your misfolded protein, unravel it, and give it another shot at folding properly. Okay? So we want to understand, how will the mean first passage time in the absence of this perturbation, how will it change when you introduce this perturbation? How does it affect the mean first passage time? So you want to write something like we wrote before, where the time it takes the process to complete with the perturbation is some time without the perturbation. But the first thing to note, right? So I want to illustrate the difficulty, right? We can't just borrow idea. We can't just take something off the shelf and just apply it to first passage time processes. It doesn't work. I want to explain why. So the first thing to notice is that we're out of equilibrium. This is a transient process. It's not in equilibrium. It's not even in a non-equilibrium steady state. It has an absorbing state. It starts, it ends. And these theories were, not designed to deal with transient processes. Another problem that we have is that perturbations are not small. Okay, if we want to be relevant, if we want to form something that is relevant to the perturbations that we see around us, we can't do with small perturbations. This is not a small perturbation to the system state. You take a misfolded protein, you open it, it's not a small perturbation. A black swan is not a small perturbation to the dynamics of financial markets. The way people perturb the training of neural networks, they change a lot of the weights that are in there that the network have learned. This is not a small perturbation.
Considering only processes where the mean exists.
So for now, yes. I will comment about this at the end. Yeah, that's a good question. Yeah. No. Okay, so small perturbations are not enough. On the other hand, we want to do linear response, so something needs to be small. It's not clear what this something should be. Okay, this is a challenge. And the last thing, how do you compute the susceptibility, right? So we're out of equilibrium. We're looking at a transient process. We're lacking standard tools like the fluctuation dissipation theorem. How do you compute the susceptibility of, perturbing the training of a neural network? How do you compute the susceptibility of something like that? Right? It's not clear. So these are the challenges. And the point is that as of now, we don't have a response theory for kinetic processes because these are challenging things to do. So we want to have something like linear response to first passage time processes, but it's not clear where to start. A hint came from one particular perturbation for which we already have a linear response theory. Actually, we have much more than that. And this particular perturbation you heard about from Satya and from Shomrita, it's called stochastic resetting. I'll just again mention what it is. You have some process here, it's a particle diffusing. It wants to get here, but at some point you reset it, okay, and it continues, and just by chance it goes to the upper basin where the process ends. But in general, it's not clear what this will do to the mean first passage time. Okay, so how will the mean first passage time change if you reset your process with some rate lambda? So this was not clear 15 years ago, but now we know everything about this, and in particular, we know how it will change in the linear response regime. So the mean first passage time of a stochastic process that is reset with some rate lambda is the mean first passage time of the underlying stochastic process without resetting, plus lambda, this rate, which is now assumed to be small, times a susceptibility. And the interesting thing is the susceptibility is completely universal. It only depends, has the same structure regardless of the underlying first passage time process that you're looking at. It only depends on the mean of the underlying first passage time process and on the variance of the underlying first passage time process. This is the only information, and once you have this information, you have the susceptibility. And the interesting thing to note here is that akin to what we know from classical statistical mechanics, fluctuations in the unperturbed first passage time, they come to predict the linear response to stochastic resetting, to this perturbation. In particular, they determine the sign of the susceptibility, whether it's negative or positive, whether the application of stochastic resetting will lower or higher your mean first passage time. Will it expedite or hinder completion? And you can see that when the standard deviation is larger than the mean, you're guaranteed that the introduction of a small resetting rate will lower the mean first passage time. Question? Yes? So the mean is infinite for Brownian motion in unbounded domains. And then you can also show, you need to treat these cases separately, but in cases where the mean diverges or the standard deviation diverges, you can show that in these cases resetting will always help, okay? But the formula will not work, hence you need to show it in a different way, okay? This formula is well defined in situations where the mean is finite. Actually, it also captures in situations where it captures in situations where the variance diverges. Over there also the resetting always work. The proof for diverging means is different, okay? But here for simplicity, I'm assuming finite mean and variance. No, because if you start from an underlying situation where the mean diverges, you're going to have a nonlinear response. At zero rate, the mean first passage time will be infinite. Okay. So, okay, but I'm going back to our setup now.
Basically, it limits this picture to say confined geometries whatsoever. You cannot go to infinite spaces.
So I will comment on this. I will comment on this later at the end. Okay? So, but it's true that for now we're assuming finite mean and variance. Okay, so I'm going back. The sign is determined by whether or not the standard deviation is larger than the mean, and this had many applications because it basically tells you when can you use stochastic resetting to expedite certain processes. I'll just mention two for which I have nice pictures and are taken from our work, but there are many examples that were given including by people sitting here for when resetting can help you. One is in search theory. You ask yourself, how should I search for a target? Should I search like the butterfly continuously until I find the target? Or like the bee, search, return, search, return? Well, depending on whether or not the standard deviation of the underlying process without going back, the way the butterfly searches, is larger or smaller than the mean, this will determine what you should do. So the separatrix, there is no definite answer to this question. You could, this could win, the butterfly can win, or the bee could win, but who wins is governed by the ratio between the standard deviation and the mean. So you have a well-defined characterization, and this well-defined characterization can be translated into an interplay between physical parameters in concrete settings. Another example, which is a little bit more recent, is coming from enhanced sampling of molecular dynamics simulations. So in computational chemistry, people are simulating. Here you have an example of a small peptide. They're simulating molecules on the computer, and they're interested in seeing transitions between different states of these molecules. For example, they start here in this conformation, and they want to see transitions to here, but it takes a long time to simulate these processes if you have large molecules. So people came up with all sorts of different ways to enhance sampling, basically speed up molecular dynamics simulations. And what we came and did is we said, okay, just observe that on top of everything you're already doing, you could add stochastic resetting if this transition, this first passage time to go from here to here, has a standard deviation, the underlying first passage time has a standard deviation that is larger than the mean. Just simply add resetting, you'll see more transitions, you'll be able to collect more statistics and characterize your system better, okay? Of course, the story is more complicated than that, but I'm just commenting on this one simple perturbation for which we know everything basically as of now. But now the question is, okay, this is good for an arbitrary first passage time process, but a particular perturbation, stochastic resetting. How do we go beyond stochastic resetting and talk about a general first passage time process with a general perturbation? So I told you the hint came from stochastic resetting, and it goes to what should be small in the linear response theory that we're doing. So stochastic resetting is not a small perturbation. It can be a huge perturbation. What was small was the rate at which it was applied. So let's consider a stochastic, but arbitrary perturbation, stochastic in the sense that it will be applied with a constant rate that is small, but the perturbation itself is going to be arbitrary, not necessarily small. Maybe I have a diffusing particle, and then I give it a big kick. But the rate at which I kick it is small. In this case, you can show something that is a generalization of what we've found for stochastic resetting. The perturbed mean first passage time, perturbed with some rate lambda, is the unperturbed mean first passage time plus lambda, the perturbation rate, times the susceptibility. And what's interesting is that the susceptibility is universal. It only depends on the mean first passage time of the process without the perturbation, on the variance of the first passage time without the perturbation, and then there's a small price to pay. You need another first moment, and this is the mean time for completion from the moment the perturbation is introduced till your first passage moment, okay? And you can see that for the case of stochastic resetting at a small rate, this guy is just the mean first passage time, and you get exactly the formula that was there. But now we can talk about arbitrary perturbations. Okay, now a question. Should I apply the perturbation? So maybe I have a first passage time process that takes, on average, 1 minute to complete. And I'm interested in making it complete faster. So what do? I go to the perturbation vendor, and I tell him, listen, give me a perturbation that can help me with this first passage time process. I want to make it complete faster. So the perturbation vendor tells me, why are you coming at the end of the day? You know, all the good perturbations, I already sold them. The only thing I have for you now is a perturbation that if you apply it, it will take your process 1 hour to complete. And because it's the end of the day and it's, I don't know, I'll give it to you at a low price. The question is, should you take it or should you not take it? So at face value, if you're only doing mean type of analysis, the answer should be no, because you have a process that on average takes us a minute to complete. Why should you, if you want to make it complete faster, perturb it with something that after the perturbation will take an hour to complete? But if you look at the susceptibility that I just showed you, you see that means are not enough. You're also sensitive to the variance in the underlying first passage time. And so if the variance is large, this guy is going to be negative regardless of how large the ratio between this tau bar, here 1 hour, over the average mean first passage time. So this can be very large, but if the variance is larger, then this will be negative. And you should apply your perturbation. So this is a little bit unintuitive, but we also had in the beginning these kind of unintuitive effects when we started thinking about stochastic resetting. Why should you take a process, erase all the progress that you've made, start all over, and still it will help you complete faster? Well, turns out that it's only because fluctuations matter, also in stochastic resetting, but it's a generalization of that. Why? Okay, so how do you prove that? One way to prove it, and this is, in my view, the most elegant proof, because it only uses elementary mathematics, is to go and utilize the inspection paradox. So the susceptibility for stochastic resetting, we showed that it can be derived from the inspection paradox. We've written a very nice viewpoint on that with Arnab and Sarah Kostinsky, who were back then postdocs at the group. But the same ideas can be generalized for arbitrary perturbations with really high school mathematics, but you need to know about the inspection paradox. So I'm just mentioning it. It's done in the paper. I'm not going to talk about this today. So this is one proof. Another proof is more straightforward. Let's do it. That's a sketch of the more straightforward proof. What do? First step. You write an equation for the perturbed first passage time. T sub lambda, the first passage time perturbed at some rate lambda. What is it? Well, the perturbation comes at a constant rate, so the perturbation time is exponential with rate lambda. And then, either of the two things will happen. Either you're going to have first passage before the perturbation occurred, then your first passage time is going to be the original first passage time, but conditioned on the fact that it happened before the perturbation. Or, you're going to perturb the process at some random time p, and then you need to add to that the completion time, which I'm denoting here by tau, but it's a function of q, the state of the system, at the moment at which the perturbation was applied. So in the example of this particle diffusing in some energy landscape, this is where I caught the particle at the moment that I turned on the field. Okay, this is q. Now what do? You take expectations. You have two terms. The first term is just the minimum between t and p. Just the minimum between the perturbation time and the first passage time. One of them is going to occur first. Take the average of that. This is always going to be a contribution to your first passage time. Now, for some trajectories, perturbations will occur before, the perturbation will occur before first passage, and then you need to add another time. So what do you need to do? You need to add this tau of q, the time it will take you to complete from the moment the perturbation has occurred, given that it caught you at state q, but you have to do three kinds of averages. One over the noise, so there are the stochastic trajectories that will take you to the target. You have to average over all of them, so hence you have this average here. One over all the moments at which perturbation can occur with the exponential weight, lambda e to the minus lambda t. And then another one over all the state space, basically over all the states at which I could catch you when the perturbation occurs. And this g of q and t is just the probability density to catch my system at state q at time t in the presence of the absorbing boundary, but before the perturbation, for the underlying process. So this is basically the propagator of the underlying process in the presence of an absorbing boundary. Okay, now what do? You observe that you can simplify this guy here and write it like 1, because P is exponentially distributed, write it like 1 minus the Laplace transform of the unperturbed first passage time evaluated at lambda over lambda. This is a term very similar to the one that we have in stochastic resetting, and this guy I just carried. And now you expand to first order, and you get the result. The only thing that is left undefined is this tau bar. I told you it's the mean time for completion from the moment the perturbation is introduced. But what is it mathematically? So I'll move this equation up. Okay, what is this tau bar? Tau bar is just the average of the average tau q. This is average with respect to the noise. But now you also need to average with respect to all the states. But with what weight? Turns out that the proper weight that you should introduce is this thing. You get it immediately when you do the first order expansion, the small lambda expansion. And this is just given by 1 over the mean first passage time integral from 0 to t, the propagator of your underlying process with an absorbing boundary dt. Okay, so this is the weight. And that's it.
Averages on the right hand side are unperturbed averages.
This one?
Previous line.
Here?
Yeah, these are unperturbed averages.
These are unperturbed averages. This is very important. So this is the mean of the unperturbed first passage time and the variance of the unperturbed first passage time. This is important because we want, from the properties of the unperturbed process, predict what will be the effect of the perturbation. Okay, so now exactly we have this linear response here. What can we do with it? Okay, so some applications. First thing that we wanted to do, we wanted to consider an example or illustrate these ideas in the context of an example where we can do everything analytically all the way through. And the example that we came up with, and of course you can come up with many different examples that are interesting to consider. We came up with something like this. You have an overdamped Brownian particle. It starts diffusing here. It wants to get in the origin. It wants to get to L. This is the target. And it starts on a linear potential that looks like this. And then at some random time, okay, with a constant rate, exponentially distributed time, but with a small lambda, I'm going to turn on a field. And this field is going to be logarithmic. So you switch from diffusion on a linear potential to diffusion on a logarithmic potential. And the question is, how will the mean first passage time respond to such activation? And in particular, will it lower or will it expedite you hitting the target or hinder? So in principle, it's not clear what will happen. If the particle catches me here where the slope is very steep, then the logarithmic potential will drag me to the target. If I'm very far away, it will take longer than the linear potential. How do you do this? Well, one way is to do it brute force, and I'll come back to that in a minute. But now we have a general tool that allows us to approach this problem and many other problems, at least get some intuition regarding the linear response to the activation of the field. So this is the susceptibility, and now actually all I need to do is plug in stuff from textbooks. What is the mean first passage time to get from here to here, from the origin to L on a linear potential for a Brownian particle? This is known. The variance is also known. What is this tau bar? Well, first, I need to understand how much time it will take a diffusing particle to get from some position x to the target L on a logarithmic potential. This is a textbook problem. It's known. You plug the result here. What is this? This is just the propagator of a Brownian particle diffusing on a linear potential in the presence of an absorbing boundary. Okay? It's also known. You plug it here. And then you do this integral. Turns out that you can do it all the way through. And you get a closed form expression for tau bar. You put it inside this susceptibility, and you get an expression for the susceptibility. I didn't write it, but I'm going to plot it. Okay? And when you plot it, you discover that there are phases here. And how to do the phase space is immediately clear when you get the susceptibility. you should have the Peclet number here, standing for the strength of the linear potential. You should have beta U0 over kBt, standing for the strength of the logarithmic potential. And there's going to be a phase where the introduction of a logarithmic field will hinder first passage time. This is where the logarithmic potential is weak, or the linear potential is strong. And there's another phase where the introduction of a logarithmic potential will expedite first passage. And this line here is known now exactly from the analysis of the susceptibility. And of course, you can generalize this for many, many other examples. But now you can also start asking more sophisticated questions, because there are going to be transitions in this problem, right? It's a naive looking problem, but all of a sudden we see that, you know, if we come from here to here, the optimal rate at which you should apply the perturbation in order to minimize the first passage time, this will change probably from 0 to some positive number. One second, I'll finish this and then I'll take a question. And this is really exactly what you see. But to get this, you need to go beyond linear response, of course. This problem is, you can do it. You can solve it exactly for every lambda, get the mean first passage time. But what I want to show you is that, you know, if you take Peclet equals 3, for example, right here, and you start walking like this, and you ask, what is the rate at which I should apply the perturbation so as to minimize the mean first passage time to the target? So you see it's 0, 0, 0, 0, 0, 0 until you hit the separatrix, and then it starts growing. Okay, and at some point, actually, beyond a certain value, it becomes infinity. This means that you should immediately switch to the logarithmic potential. Similarly, for Peclet equals 2.5, but here for Peclet equal 1.3, you see that there's a jump. So you have both continuous and discontinuous transitions in this naive-looking problem for the optimal resetting rate. Please.
So are you assuming that you are just switching only once? Because in principle, it can happen many times. And
So in this problem, okay, once you switched, you switched, okay.
once, and then
But I'm defining the perturbation in the following way. The perturbation is to go to this field, okay. So maybe you can. So basically, I switched the first time, but then, you know, even if it happens again, I'm going to the same field, so it doesn't matter.
So you're just
So it's yes.
the same one. So it's like
Yeah.
from the log, you're not
Yeah.
doing anything else.
Yeah, exactly. So this is the perturbation in this case, okay? Because we wanted something that we can, you know, we can do everything and is fully tractable. But of course, the theory is not limited to that. Okay. So here we could do everything analytically, but there are situations, of course, where you know, it's not clear how to do things analytically. One of them is the training of neural networks. The problem over there, you know, people are applying all sorts of perturbations. They don't know what is going to be the effect of these perturbations. So they try. But if they try, right, this defeats the purpose. Because, you know, things that will work, you will know that they will work only after you've invested time in exploring them. What would have been nice is to predict ahead of time what perturbation will help you train the network faster. And this will save money and a lot of resources. And I'm not going into the details of this problem. It's described in this paper. But what you can see is that, okay, there was one case, stochastic resetting. So this is one perturbation that you can apply to the training of neural networks, where we know everything, basically. So this line is theoretical. These are measurements, right? Simulations, very hard simulations. Each box here is a very hard simulation that you need to do. We could predict this line without doing the simulations, just from few runs of the system that is unperturbed. So this is great because you know what will be the effect of stochastic resetting. But now we can do it for any perturbation, at least to first order, and note that I've switched the axis here. I've considered small rate. Here, the perturbation is applied in constant time intervals. So we're actually, rare is large p. P is the number of epochs until I apply my perturbation. Okay, so we're expanding around infinity. So we're predicting from here. Okay, and you can see that we can tell apart this from this. So this is S&P is this is partial resetting. So it's a strategy where you reset some of the weights. And this is a strategy, shrink and perturb, where you scale some of the weights and then add some noise to the others. And you can identify, without doing all these expensive simulations, this is something that you would not be able to do otherwise, just from measuring, basically measuring these parameters here. Previously, we computed them. They were analytically computable, but I can also measure them. T average, tau bar, this sigma, once, and then predict forward for higher rates. Just by measuring these things, we can make these predictions and then actually design useful perturbations. And you see here that actually stochastic resetting is the worst perturbation. It just tells you that there are better things out there and we should be looking for them. Okay, I want to finish with a word on inference. Okay, so this is now using this framework in reverse. So far, I talked about prediction. So we wanted to know the mean first passage time of the perturbed process. This was unknown. So we said, okay, let's treat this thing as something that is known. I know my tau bar, or I can measure it, or I can either measure it or compute it. I know the mean of the unperturbed process, the standard deviation. From this, I'm going to predict. But of course, we can also switch it around. I can say, okay, let's measure this guy. Let's do an experiment. Measure how the mean, the perturbed mean, what it is. Suppose I know this guy, the mean without the perturbation. And then I will extract this guy by plotting versus lambda and extracting the slope. And if I control my perturbation, I control tau bar. The thing I'm going to extract is the variance in the mean first passage time. And why is it interesting? It's interesting because it opens a way to do something that was considered to be completely impossible. And this is to extract single molecule fluctuations from bulk measurements. So I'll give you an example. You have a scenario where molecules are being synthesized and then degraded. If you measure the concentration, the steady state concentration, it's not sensitive to fluctuations in the lifetime of the molecule. It's only sensitive to the mean synthesis time and the mean degradation time. So you need single molecule measurements, or at least this is what people thought, in order to decide what is the variance in the lifetime, what is the distribution of the lifetime, and so on and so forth. But now, we know that the change in the mean lifetime of this molecule, if I'm going to perturb this first passage time process, the first passage time process is now how much time it takes a molecule to go from the moment it was synthesized to the moment it was degraded. If I perturb it, say by introducing a small concentration of an annihilator, then the change in the mean lifetime, and hence the change in the steady state concentration of these molecules, is going to be sensitive to fluctuations in the unperturbed first passage, in the unperturbed first passage time, which is here the lifetime of the molecule. So I can extract in this way, just by fitting lines to concentration versus steady state concentration of this molecule versus the steady state concentration of the annihilator, I can extract the variance in the lifetime of this molecule. And in fact, I can also go much beyond that, and this is explained in the paper, and extract the full lifetime distributions from concentration measurements without needing single molecule experiments, which are extremely hard to perform. Conclusions. I've introduced a theory that allows us to predict how the mean first passage time is influenced by perturbations, general perturbations, and have shown that the susceptibility, this thing right here, is completely universal. It has this form, and I've also discussed some applications. I'll just end with 2 remarks. One remark, we considered constant rate at which the, or exponential time at which the perturbation comes. We can also generalize to non-exponential perturbation timers and going to the rare limit in their application. What you get is actually the same thing, but with an effective rate, okay? The details I can discuss. We can also go or generalize to situations where the variance here of the underlying first passage time diverges. In this case, you have a nonlinear response, but it's still universal. It's universal in the sense that it doesn't care about the perturbation that you apply. As long as tau bar is finite, the response will not care about the perturbation. It will only care about properties of the tail, the heavy tail of your first passage time distribution, and it will look like this. The case of diverging means is slightly more complicated and slightly less universal. We're working on it right now. And with this, I would like to end. So thank you very much. And I would like to again mention Tomer, who is an extremely talented PhD student. So he's the linear response team, one man's team, and my other group members, Itamar Bara and Ido. Thank you.
Okay, thank you very much. I mean, but we have time maybe for one question, an urgent question. Okay, so maybe that's not the case. So thank you and all. Well, okay, you go ahead. I mean,
you know, I was just thinking if you can this perturbation can be this talk, this Gregory's talk where you change this diffusion coefficient, for example. Does your thing? I mean, is it going to work? I mean,
yes. So okay. What do you need to do then? Okay, you have to take into account. This tau bar is going to encompass all the complexity from the moment the perturbation has been introduced. Okay? So basically, you can think about 2 steps. A first step before the introduction, the first introduction of the perturbation, and then you know it's going to switch and switch multiple times. All of this goes into tau bar. But the interesting thing is, there are a lot of details that seem to matter. Turns out that they all feed into a single parameter, and if you know the single parameter, you're done.
that's also the mean first passage time, right?
This is the mean first passage time from the moment the perturbation has been introduced, and recall that it's a triple average actually, because the position is stochastic, the time is stochastic, there's noise.
okay, so let's thank Shlomi and all speakers of this morning session. So I close the session. I mean, so maybe now you have some announcement?
Quick announcement. Yeah. So I have just a quick announcement. So today, after the end of the last talk at 6 o'clock, I've arranged for a visit